Share my screen. So what we have here, number 8 is the one that we're going to focus on. So one card is drawn from an ordinary deck of cards. Find the probabilities of drawing the following cards. So we've got A, which is an 8 or a 5. B, a red card or an 8. C, a 3 or a red 2. D, a heart or a black card. And E, a face card or a heart. Send me the probabilities as fractions in reduced form. So for A, getting an 8 or a 5, those don't have anything in common. So it's going to be 450 seconds, excuse me, plus 450 seconds. Again, this is the probability of an 8. This is the probability of a 4, giving us 50 seconds or 2/13, right? If we look at B, a red card or an 8, red, there is half the deck. So we have 26 out of 52 for red. Plus the 8s, which are 4 out of 52. But then we have to take off the 2 red 8s that we counted twice, giving us 28 out of 52, or what does this reduce to? What is it? 7/13. So C says a 3 or a red 2. So 3s is 4 out of 52, right? And the red 2, there's only 2 of those. So we end up with 6 out of 52, or 3/28. Now D is a heart or a black. Hearts, there are 13 hearts. Blacks, there are 26, which is half the deck, excuse me. And hearts are red, so there's not any overlap there that we have to worry about. So this is going to give us 39 out of 52, or 3/4. And then E, which is a face card or a heart. So faces, there are 12 face cards in the deck. There are 13 hearts in the deck. And there, whoops, there should not be a plus here. There are 3 heart faces, which gives us 22 out of 52, or 11 out of 26. Okay. So let's look at the next question. Let's look at number 9. Number 9 says a pair of dice is rolled. What is the probability of getting a sum of 8? Probability of getting a sum of 8. Okay, so if we're looking at a sum of 8, so how do we make 8? We're rolling 2 dice, right? And there's the numbers 1 through 6. So we can make an 8 by doing a 3 and a 5, or a 5 and a 3. We can do a 2 and a 6, or a 6 and a 2, or we can have 2 4s, which gives us 1, 2, 3, 4, 5 possible outcomes out of 36 total sums, assuming that order matters, right? Whatever we get on the first die is important versus what we get on the second die. So now thinking about the same die, let's look at number 10. It says, what is the probability of getting a either a sum of 7 or at least 1 6 on the roll. Okay, so if we think about, we want a sum of 7 or at least 1 6. So let's look at our table for if we're doing we're rolling these dice. So we can have a 1, 2, 3, 4, 5, or 6. 1, 2, 3, 4, 5, or 6. Okay. So at least 1 6 is going to happen here and here. Okay. So if we look at the sums that are there, we have 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. So probability of the sum of 7. So sum of 7 happens along this diagonal here. Okay. So we can see that there's 1, 2, 3, 4, 5, 6 ways to get a sum of 7 out of 36. The probability of at least 1 6. How many numbers does the blue cover? So we have 6 vertically, and we would have 6 horizontally, but remember they overlap at 12. So we end up with 11 out of 36. And then we have the idea of the probability of a sum of 7 and 1 6. And that's where they're overlapping here in these two places, which is 2 out of 36. So we're going to have 6 out of 36 plus 11 out of 36 minus 2 out of 36, which gives us, what did I come up with? 15 out of 36 or 5/12. So I really like to draw the diagram. It doesn't take that long, and especially when you're doing this at home, right? You're going to have all the time in the world. So I like to draw the diagram, and then you're able to color those spots and actually identify what's overlapping and all of that. Okay, so number 11, it says 2 cards are drawn without replacement from an ordinary deck. Find the probability that the second is not, a 7, given that the first card is not a 7. So let me try to make it a little easier to read. Again, Two cards are drawn without replacement for an ordinary deck. Find the probability that the second is not a 7, given that the first is not a 7. So I'm going to encourage you to draw a tree diagram for this, okay? Sorry, Isabel. Okay, so I just wanted to have you give it some time to think about it. So when we think about, we're drawing the cards, and we want to know what is the probability we're going to get a second 7, depending on the fact that we didn't get a first 7. So when you think about a pack of cards, right, there's 52 cards, there are 4 7s in the card. So we're going to have a probability here of 4 out of 52 if we draw a 7. If we don't draw a 7, then it's going to be 48 out of 52, right? So that's just the probability of getting a 7 first. Okay, so then we go to the next outcome. So if we drew a 7 first, and we draw a second 7 again, it's going to be 3 out of 51 for this stage versus 48 out of 51 for that stage. If we go down to, if we didn't draw a 7 first, but we draw a 7 second, there's still 4 7s there, but we only have 51 cards. And then not drawing a 7 second would be 47 out of 51. So the probability of second, not 7, given, so remember that vertical line means given, first, not 7, is this outcome right here. It's the 47 out of 51. So this kind of speaks back to when we were talking about these tree diagrams to begin with. This is conditional probability. So if I have events A and B, so this is event A, and this is event not A, right? So we can actually think about this as in terms of probability. This will make more sense. The probability of A and the probability of not A, right? So then this outcome right here is the probability of B given A. This is the probability of not B given A. And here we're going to have the probability of B given not A, and then the probability of not B given not A. When we multiply these through, okay, we move through our tree diagram, we're multiplying these together. So the probability of A times the probability of B given not, or given A, which is going to be the probability of A intersecting B. This one is going to be the probability of A times the probability of B not A, which gives us probability of A intersecting not B. This one's going to be the probability of not A intersecting B, and the probability of not A intersecting not B. So when we think about, if we're trying to find the probability of just say, now this is going beyond what this question is asking, I just want to review all of this. If we were looking at, let's say we wanted to find the probability of A happening in this situation, we'd have to add up the probability of A intersecting B and the probability of A intersecting not B, because those are both the events that have A happening in them. If, say, we wanted the probability of B, then we would be adding the probability of A intersecting B plus the probability of not A intersecting B. So this goes back to those conditional probabilities that we were talking about in chapter 7, I think, at the end there. Maybe we were into chapter 8. I always forget where all this stuff ends up. Oh no, let's see, 8 random variables. So this goes back to like 7.6. Okay, so if you look at Bayes' theorem, Bayes theorem is part of this, and 7.5 conditional probability. All of those those in 7.4 is all part of that, okay? But you're going to see a diagram like this in our notes from 7.5. There's a diagram for that, and also in 7.6. Okay, so what we want to think about is how do these things come out? Like, what do they mean? Okay, so we're doing our first branch, and then off of that we'll do our next branch. Okay, so again, in this situation, if we go back to what is the probability that we get not a 7-second, given that it happened, we didn't get a 7 first, that's referring to just this location. And so if I wanted to know what is the probability of not 7 first and second, and say they were asking that question, then I would be taking these two probabilities and multiplying them together, because that's an intersection of the event. We're saying, what is the probability that both of those happen? But because it's just saying, let's look at that last part of our tree diagram, what is the probability that that second thing happens, given that the first thing didn't happen as well? That's why we're just using that individual probability there. We're not multiplying anything together. Does that make sense? Maybe, kind of, hopefully. All right, so what is the last? So this kind of, number 12 kind of goes into that as well. So we can talk about that one together. Get back to my notes. Okay, so let's blow this up a little bit. So we have this whole big table here, right? And so it says the following table lists the passengers who were on a cruise ship that sank and the number of passengers who survived according to the class of ticket. So with children, women, men, total, how many were on, how many survived, first class, second class, third class. So part A says, given that the survivor was from third class, what is the probability that the survivor was a child? So they're saying, remember, the given part establishes our population, okay? So we're looking at third class only. So that's these people right here. Just this row. So there was 631 total in third class, but only 184 survived. So the probability of child survived given survivor from third class. This seems, so the total number of survivors for third class was 184, and probably that was a child that was one of those survivors. We would go back here and look at child for third class is 28. So we would have 28 out of 184 for that. So again, the given part is what establishes our population that we're dealing with, and then we apply the next conditional statement to that. And then part B says, given that a woman survived, what is the probability that she was in third class? So now we're looking at probability that woman survived. Oops. I'm stating this wrong. What is the probability? woman in third class given men survived. So now we're looking at all women who survived, because that is what is establishing our group, our population. Was that a woman survived. So if we look at our table, how many women survived? Well, 295 women survived. How many of those were in third class? 80 of them. And so we're probably the woman who survived was in third class is 80 out of 295. So just some additional things that I would consider studying, that I've looked at the, I don't remember if I had these on my list. Let me look really fast. Go back to my list. Don't forget, we talked about solving systems using matrices. And there's another one. So again, conditional probability, like what we have here. Bayes theorem, go back and look over Bayes theorem is another suggestion I have. I talked about expected value already, so make sure you remember, you go over what that is. Because I got the final and I looked through it. I don't think there's anything else that we didn't already have on our list. But again, I said this already and I'll say it again. Just go over those 3 reviews from the first 3 exams that we had, and make sure that, you look over all of that stuff. So the final will release Monday morning at 8 a.m. And so you'll be able to work on it starting Monday. It'll be due, did I already say when it was due? Let me see if it says in the announcements. So it's going to release Monday morning, and it'll be due, so I guess I have it set to release at 12 a.m. Monday morning. And it'll be due Wednesday night by midnight. And you can use all of your notes. You can use everything that you have in the class. You just can't use any websites other than, like, you can use graphing websites like Desmos, but you can't use any help websites, obviously, or anything like that. So it is take home. I'm going to have you just record your work on a separate sheet of paper. So make sure that that's all numbered, but all these instructions are in the final as well. So any last questions for me before we go? All right. Well, thank you so much. It's been a great semester. Please email me if you do have any questions between now and when you need to turn in your final. And thank you. Have a good break. Okay. Bye.